Hello everyone, this is group number 10 and we are present here for the video presentation of Advanced Algorithm Design and Analysis IA2. The topic for our IA2 is Push Relabel for Max Network Flow. These are the group members. So let's start with the introduction of the topic. So Push Relabel algorithm was described by Dr. Andrew Goldberg and Robert Tarzan, and it is considered as the fastest maximum flow algorithm. It is more efficient than Ford-Fulkerson algorithm because it runs in order of v square e time. So the intuition behind the push relabel algorithm is that we consider a fluid flow problem. That is, the edges would be considered as water pipes and the nodes would be considered as the joints or junctions. So the source in this case is considered to be at the highest level initially, and it will send water to all the adjacent nodes. So once a node has excess water, it pushes water to a smaller height node. The terms like excess, source, sink would be described in detail in the upcoming slides. So now if the water is trapped at a vertex, then the vertex would be relabeled. Relabeled meaning that the height of the vertex would be increased. So let us see the problem statement. In the problem of push relabel, we would be given a graph with source and sink nodes, and we would like to compute the maximum rate at which a fluid can flow from the source to the sink. So here the node S is the source and T is considered to be the sink. So the rate of flow through each edge of the graph. So these are the two things which we have to compute. So as you can see on the edge, there are two values, 5, 2. So in this case, the first value, which is 5, it stands for the flow capacity. And the second value, 2, this stands for the current flow rate in the edge. So now let us see the intuition behind the push relabel algorithm.
Hello all, myself Siddharth Mishra. Now let's talk about the intuition. So our main goal is to find the maximum flow from the source in a sink. So in the Ford-Fulkerson algorithm, it used to examine the entire residual network to find the augmenting path, and that was an iterative process. But in case of the push relabel algorithm, it works on a one vertex at a time. So by looking at this particular figure, we can see this is a source and this is a sink, and in between there is a network of a pipe and a joints. So the pipe will be termed as the edges and the joints will be termed as the vertices. In case of the push relabel algorithm, the vertices mainly holds the two properties. First of all is that vertices can accommodate the excess flow. Second one is that each vertex, its reservoir and all its pipe connection are on a particular platform whose height increases as the algorithm progresses. Now let's talk about the important terms. So we are having a source and a sink in a network, and our goal is to find the maximum flow in between source and a sink. And talking about the capacity and a flow, every edge in a network has a flow passing through the edge, and capacity is the maximum allowable flow. Excess and active node. Excess is the difference of the total incoming flow and the total outgoing flow, and a vertex having some excess flow except the source and a sink is called as an active node. Now talking about the height, each vertices will be given a height variable. So initially the source will be given the maximum height and the sink will be given the minimum height. An active node has to push its excess flow to its neighboring vertices so to normalize the incoming flow and total outgoing flow. Now to push to a vertex, the height needs to be updated. That is known as a relabel operation.
Now coming on to the push relabel algorithm. The first step is to initialize the preflows, which includes initializing the height of all the vertices as 0, initializing the height of source vertex as v, which is equal to the total number of vertices in the graph, and then initialize the excess flow of all the vertices as 0. Then, for all neighboring vertices of source node, flow and excess flow will be equal to the capacity of the connecting source neighbor edge. Once the preflow operation is completed, whenever we find a vertex with excess flow, we will either perform the push operation or the relabel operation. And at the end, all the vertices should have zero excess flow except the target vertex. And then we will return the maximum flow obtained at the target vertex. And coming on to the pseudocode of push relabel algorithm, which takes vertex and edge as the graph input, C as the cost matrix, S and T as source and target vertex respectively. The first two steps indicate initializing the preflow, that is initializing the height of all vertex and flow of all the edges connected to source vertex. Then for all vertex except the target vertex, if they have an excess flow greater than 0, and if the edge between its connecting neighbors belong to the residual network and satisfy height constraints, we perform the push forward or backward operation respectively. Else we perform the relabel operation and finally return the maximum flow value at target vertex.
Hello everyone, my name is Parsha. So here we consider a graph. So here we have S as our source vertex and sink as T as a sink vertex. So the height of the source vertex is always equal to the number of vertices in that particular graph. For each of the other vertices, we have height and excess flow as 0 initially. So each edge has its capacity and the flow. So the capacity is represented as the maximum capacity that can flow through that particular vertices. So initially the flow of each of the edge is 0. So let's move on to the each of the step one by one. So here is the step 1. So here we have source vertex S and the capacity flowing from S to A is 10 and S to C is 12. So we have flow that we are pushing from S to A is 10 and S to C is 12. So A and C are now active vertices. Now we move on to the second step where we have C as we have considered as C, and from C to D we have flow as 6 and C to A as 5. So we have excess flow as 12 and the flow going out as 11. So we have one excess flow remaining. So we now A, C and D are the active vertices, and height is the number of excess flow given through the edges. So here we have two vertices, so the height is 2. Now in the step 3 we push back one excess flow from C, so A and D are now active vertices and the excess flow of E becomes 0, and the height is increased because we have pushed back to the source vertex, so height is becoming 7. And now in the step 4 we consider A as our vertices and the incoming flow is 15. So the outgoing flow is also 15, and now the excess flow is 0. So now B and D are the only active vertices.
So coming to step 5, B has an excess of 15. So we choose node B. We increase the height of node B by 1 and we push 3 from B to D. We again increase the height of node B by 1 and we push 8 from B to D. Now excess at B is 4 and B and D are active nodes. Step 6. So node B has still excess of 4 remaining and it cannot push it further. So we increase the height of B by 1 and we push back excess of 4 from node B to node A. Now excess at A becomes 4 and A and D are active nodes. Step 7. So we choose node A, we increase the height of node A by 1 greater than height of node S. So the height becomes 7 and we push back the excess 4 from node A to node S. Now excess at A becomes 0 and the only active node remaining is node D. Step 8. So now we choose node D. We increase the height of node D by 1 and we push 14 from D to D. Now excess at D becomes 17 and there are no active nodes remaining. So the max flow from S to T is 70, which is nothing but the excess flow at sink. So one application of pre-flow push algorithm is the minimum cut, which is nothing but a cut which is a set of edges that divides the graph into two parts such that the sum of capacities of the edges lying on the cut is minimum. So here the cut is BT, BD and CD. So that's all for the video. Thank you.